Tonight, the sky above us seems timeless, but there was an age when no star had ever opened its eyes. The universe was already vast, yet every horizon waited in a darkness deeper than any ordinary night. No galaxy turned in silence, no planet crossed an orbit, and no distant sun cast light across space. This first chapter begins before the cosmic dawn, when the ingredients of everything existed without a single flame. To reach that forgotten era, we must travel backward through nearly 13.8 billion years of expanding space. The journey does not lead toward one special place, because the early universe was happening everywhere at once. Every region we see today was once compressed into a hotter, denser, and far more uniform cosmic beginning. Space itself expanded, carrying matter and radiation apart while slowly lowering the temperature of the young universe. During its earliest moments, the universe was not dark in the peaceful way we understand darkness now. It was filled with intense radiation and a restless sea of particles moving through extraordinary heat. Light could not travel freely because charged particles scattered photons again and again through the glowing plasma. The cosmos resembled an endless luminous fog, brilliant in every direction but transparent in none. As expansion continued, the fierce heat weakened, and simple atomic nuclei began to remain stable. Most of the ordinary matter became hydrogen, with helium forming the second great reservoir of primordial gas. Tiny traces of lithium also appeared, but the heavier elements familiar on Earth did not yet exist. There was no carbon for life, no oxygen for oceans, and no iron for the cores of future worlds. For hundreds of thousands of years, electrons still moved freely among the nuclei and kept the universe opaque. Then the temperature fell enough for electrons to settle into lasting bonds with hydrogen and helium nuclei, neutral atoms formed across the cosmos, and photons finally escaped the endless collisions that had trapped them. Those ancient photons still surround us today as the faint afterglow called the cosmic microwave background. The release of that light marks a quiet boundary between the glowing early plasma and the darkness that followed. Once the afterglow streamed away, no stars existed to replace it with new points of visible light. The universe entered the cosmic dark ages, a period lasting tens or perhaps hundreds of millions of years. It was not empty, but almost everything within it remained cold, simple, and hidden from any imagined observer. Across this darkness, hydrogen and helium drifted through space in clouds that were nearly smooth but not perfectly smooth. Small differences in density had survived from the earliest moments and were preserved in the ancient afterglow. Some regions held slightly more matter than average, while neighboring regions held slightly less. These modest imbalances became the seeds from which every later star, galaxy, cluster, and cosmic structure would grow. Ordinary gas was only part of the story because most matter did not shine or interact strongly with light. This unseen substance, known as dark matter, revealed itself through gravity rather than through color or brightness. According to our current understanding, dark matter began gathering into invisible halos before ordinary gas formed stars. Its gravity created deepening wells in space, giving wandering atoms places where they could slowly collect. Gravity worked without urgency, pulling a little more matter toward every region that was already slightly dense. As material accumulated, the stronger attraction drew in still more gas and dark matter from the surrounding universe. Over immense stretches of time, tiny irregularities grew into a web of filaments, knots, and widening empty regions. The first stars would not appear randomly, but inside the densest knots of this emerging cosmic web, within a young dark matter halo, primordial gas fell inward and converted some of its motion into heat. Gravity wanted the cloud to contract, yet rising pressure resisted the collapse and pushed outward. For a star to form, the gas needed a way to lose enough heat for gravity to keep winning. This cooling problem became one of the decisive challenges on the road toward the first light. Modern star-forming clouds cool efficiently because they contain dust and many heavy elements forged by older stars. The first clouds had none of those advantages, because no previous generation of stars had enriched them. Almost every available atom was hydrogen or helium, and both could be stubborn coolants under primordial conditions. The dark universe needed a simpler molecule to open a narrow path toward collapse. In some dense regions, pairs of hydrogen atoms joined to form small amounts of molecular hydrogen. These molecules could absorb energy from the gas and release it as faint infrared radiation. Each escaping photon carried away a little heat, allowing the cloud to contract into a smaller volume. Cooling was slow and limited, but it was enough to change the future of the universe. As a cloud contracted, it spun faster because even a tiny original rotation became concentrated inward. Broad streams of gas twisted into flattened structures and fed denser clumps near the center. Turbulence crossed the cloud, shocks compressed it, and gravity tested whether each clump could remain bound. Some clumps dispersed, while others passed a threshold beyond which continued collapse became extremely difficult to stop. At the heart of a successful clump, density rose until the gas became opaque to much of its own radiation. Heat built again, pressure increased, and a compact protostar began taking shape before nuclear fusion had started. Material continued falling from the surrounding cloud, adding mass through a thick and rapidly changing envelope. The first stellar embryos grew in darkness, hidden inside the very gas that was creating them. Scientists do not yet know the full range of masses produced by these earliest star-forming systems. Simulations suggest that many first stars may have become far more massive than the Sunday. Some clouds may also have fragmented into small groups, producing companions rather than one solitary giant. The details remain uncertain because no telescope has yet captured an individual first star directly. Whatever their exact masses, these objects formed from material almost untouched since the beginning of cosmic history. Astronomers call this theoretical first generation population 3, even though it came before populations 1 and 2. The unusual numbering reflects the order in which stellar populations were recognized, not the order in which they formed. Population 3 stars contain virtually no elements heavier than lithium when their lives began. A growing protostar pulled gas inward while radiation and pressure pushed against the incoming flow. The struggle intensified as the central temperature climbed to millions of degrees under the weight of overlying matter. At last, hydrogen nuclei began fusing into helium and released energy from the compact stellar core. In that instant, a true star ignited where the universe had known only darkness. The first ignition was probably not one dramatic flash visible across the entire cosmos. Different halos reached the necessary conditions at different times and in widely separated regions of space. One by one, then in growing numbers, isolated furnaces appeared within the vast neutral fog. The cosmic dawn was a gradual awakening, scattered across distances that no single observer could have crossed. These first stars likely burned hotter and bluer than most stars shining in the universe today. With few heavy elements to block escaping energy, their surfaces could reach extraordinary temperatures. Their ultraviolet light flooded nearby gas and stripped electrons from some surrounding hydrogen atoms. Each star created a glowing bubble of ionized gas inside the otherwise neutral cosmic night. Inside those bubbles, the environment changed quickly as radiation, heated gas, and altered future star formation. Some nearby clouds were dispersed, delaying collapse by removing the cool material they needed. In other places, expanding fronts compressed gas and may have encouraged new pockets of density. The first light did more than illuminate space, because it began reshaping the conditions from which later light would arise. The stars also produced a new background of radiation that traveled far beyond their immediate neighborhoods. Much of that light encountered neutral hydrogen, which absorbed particular wavelengths and concealed the sources behind a fog. The early universe, therefore, became bright locally while remaining difficult to see across great distances. Light had returned, but the cosmos was still learning how to become transparent again. No human eye could have watched this dawn, and even our greatest telescopes approach it only indirectly. The farther we look into space, the farther we look into the past, because light requires time to reach us. Ancient galaxies appear as they were when the universe was only a small fraction of its present age. The first individual stars lie deeper still, faint and red-shifted by the expansion that stretched their traveling light. Astronomers search for their fingerprints in old radiation, primitive galaxies, and the chemical patterns of ancient stars. They also build computer simulations that combine gravity, gas motion, chemistry, cooling, radiation, and cosmic expansion. Each method illuminates part of the story, but every answer arrives with boundaries and uncertainty. The first stars belong to a frontier where evidence, physical law, and careful imagination must work together. The James Webb Space Telescope can study remarkably early galaxies, yet finding the first stellar generation remains difficult. A single primordial star would usually be too faint and too distant to separate from its surroundings. Rare gravitational lenses may someday magnify such a source, bending its light through the gravity of nearer matter. Until then, scientists infer these stars through the changes they left in gas, galaxies, and later generations. As cosmic expansion carried first starlight toward us, the waves were stretched to longer and longer wavelengths. Radiation born as ultraviolet light can arrive today in the infrared, far beyond the range of human vision. Infrared observatories are therefore essential when astronomers search for the oldest visible structures in the universe. Yet even these instruments usually see collections of stars rather than the single primordial stars hidden within them. Researchers compare early galaxy spectra with models that predict how metal-free stars should color and ionize their surroundings. A promising signal may suggest an unusual stellar population, but several younger or dustier sources can imitate it. Claims must survive repeated observations, independent analysis, and careful tests against less dramatic explanations. The mystery endures not because science has failed, but because the evidence arrives across an almost unimaginable distance. Long before familiar spiral galaxies existed, the first stars gathered inside small and irregular structures. Their host halos merged with neighbors, drawing together gas, stars, and dark matter through relentless gravity. These early assemblies were modest compared with the Milky Way, but they carried the foundations of galactic history. The night was no longer perfectly dark, and the first islands of light were beginning to find one another. The first stars had opened a door, but they could not remain shining for very long. Massive stars consume their nuclear fuel rapidly, living brilliant lives that may end after only a few million years. Their deaths would forge and scatter the first substantial supplies of carbon, oxygen, silicon, iron, and other heavy elements. In the next chapter, those stellar endings will become the beginning of richer stars, larger systems, and the first galaxies. The first stars entered a universe that had never experienced concentrated light, heat, or nuclear fire. Their arrival ended the deepest darkness, but their greatest transformation would come when their brilliant lives were over. Inside their cores, simple hydrogen was being rearranged into elements the young cosmos had never possessed. The first light was already preparing the universe for its first great wave of destruction and renewal. Many primordial stars may have contained dozens or even hundreds of times the mass of the Sunday. Their immense gravity compressed their centers to extreme temperatures and forced nuclear reactions to proceed with astonishing speed. A star with greater mass does not simply receive more fuel, because it also burns that fuel much faster. Some of the brightest first stars may have survived for only a few million quiet and violent years. For most of their lives, these stars fused hydrogen nuclei into helium deep inside their central cores. The energy released by fusion created outward pressure that resisted the continuous inward pull of gravity. This balance allowed each star to remain luminous and stable while enormous amounts of energy escaped into space. Yet every stable moment moved the star closer to the day when its central hydrogen would be exhausted. When hydrogen became scarce in the core, gravity compressed the center again, and raised its temperature further. Helium nuclei could then fuse into carbon, opening a new stage in the internal life of the star. In sufficiently massive stars, carbon was followed by oxygen, neon, magnesium, silicon, and increasingly heavy nuclei. The stellar interior became a layered furnace, with different elements burning at different depths and temperatures. Each new stage released less usable energy and usually lasted for a shorter time than the stage before. Hydrogen burning could continue for millions of years, while the final reactions might last only days. Eventually, some stellar cores accumulated iron, an element that cannot provide energy through ordinary fusion. Once the core could no longer support itself, the ancient balance between pressure and gravity abruptly failed. The central region collapsed inward at tremendous speed, compressing matter beyond anything found in an ordinary star. Layers above the core followed, falling toward the center until they encountered a rapidly changing wall of dense matter. Under the right conditions, the collapse reversed part of its motion and launched a shock through the star. A supernova then tore the stellar envelope apart and scattered its newly forged material into the surrounding night. Not every primordial star reached its end through the same physical pathway or produced the same explosion. The final outcome depended strongly on mass, rotation, internal mixing, and the amount of material lost during life. Some stars may have produced ordinary core collapse supernovas and left neutron stars or black holes behind. Others may have vanished almost directly into black holes, releasing little of their heavy elements into space. A particularly massive star could enter an even stranger regime known as pair instability. In its intensely hot interior, energetic photons could transform into pairs of particles and weaken the supporting pressure. The core would contract, nuclear burning would accelerate, and an enormous thermonuclear explosion could follow. In a complete pair instability supernova, the entire star could be destroyed without leaving any compact remnant. Such explosions remain theoretical candidates for some first stars, rather than events astronomers have identified with certainty. Their chemical products should appear in distinctive proportions, unlike those created by many ordinary stellar deaths. Astronomers search for those patterns in extremely old stars that formed from gas enriched by earlier generations. The evidence is subtle, because countless later explosions mix their own elements into the same cosmic reservoirs. Whether dramatic or nearly silent, each stellar ending altered the balance of matter in its local environment. Explosions drove shock waves through primordial gas and heated regions far beyond the original stellar surface. Material that had once been trapped inside a core expanded outward at thousands of kilometers per second. For the first time, carbon, oxygen, silicon, calcium, and iron began spreading widely through interstellar space. These elements were rare at first, diluted inside enormous volumes of hydrogen and helium. Even a tiny amount, however, could change the way a gas cloud absorbed, released, and transported energy. Atoms such as carbon and oxygen offered new pathways for cooling that primordial gas had never possessed. The deaths of the first stars therefore changed the conditions under which all later stars would form. As enriched gas lost heat more efficiently, gravity could compress it into smaller and denser fragments. Instead of producing only a few massive objects, a cloud could divide into many smaller stellar embryos. The earliest enriched star clusters may have contained stars across a broader range of masses. Some were still enormous, while others were small enough to burn slowly for billions of years. A low-mass star uses its hydrogen with patience and can survive for nearly the entire age of the universe. If such stars formed soon after the first supernovas, a few may still exist in the Milky Way today. They would not be true population 3 stars, because their gas already contained traces of heavier elements, yet their atmospheres could preserve a chemical memory of the first stellar explosions that came before them. Astronomers examine ancient stars by separating their light into the subtle patterns known as spectra. Dark and bright features within a spectrum reveal which elements are present in a stellar atmosphere. Unusual combinations can suggest that the star inherited material from only one or a few ancient supernovas. This practice is often called stellar archaeology because present stars are used to reconstruct a vanished cosmic past. The first enriched stars did not appear in peaceful isolation from the explosions that created their material. A supernova shock could push gas outward and temporarily empty a small halo of its star-forming fuel. Later, gravity might draw some of that enriched material back toward the same dark matter structure. In other cases, the expanding debris could mix with neighboring clouds and seed entirely different halos. The early universe was therefore a landscape of repeated collapse, ignition, disruption, cooling, and renewed collapse. Each cycle increased the chemical complexity of the gas, although enrichment remained uneven across enormous distances. Some regions received metals early, while nearby pockets may have remained almost completely primordial for much longer. For a time, first-generation and later-generation star formation may have occurred within the same broad era. Meanwhile, the small dark matter halos that hosted the earliest stars continued moving through the growing cosmic web. Gravity drew neighboring halos together, increasing their speed as the distance between them slowly narrowed. When halos merged, their gas streams collided, their stars mixed, and their combined gravity deepened. These mergers assembled increasingly large structures from the smaller fragments that had formed first. The earliest galaxies were probably irregular, compact, and far less orderly than familiar spiral galaxies. They contained turbulent gas, young stars, dark matter, and the scattered remains of repeated stellar explosions. Their shapes changed rapidly as they consumed gas, expelled material, and collided with nearby systems. A galaxy in this era was not a finished object, but a temporary arrangement within continuous growth. Fresh gas flowed along the filaments of the cosmic web and entered the gravitational wells of young galaxies. Some streams remained cool enough to penetrate deeply before turbulence and radiation disrupted their motion. Where gas accumulated quickly, intense episodes of star formation could illuminate an entire compact system. These early starbursts filled the darkness with clusters of blue stars rather than isolated points of light. The growing stellar population produced more ultraviolet radiation and enlarged the ionized regions around young galaxies. Supernovas added heat, motion, and heavy elements to the gas surrounding each active system. Radiation encouraged collapse in some clouds while preventing it in others, depending on distance, density, and timing. Galaxy formation was shaped by constant feedback between gravity, gas, stars, explosions, and escaping light. The first stellar deaths may also have planted black holes inside some of the earliest galaxies. A massive primordial star could collapse into a black hole containing many times the mass of the Sunday. Other proposed pathways could produce heavier seeds through the direct collapse of enormous gas clouds. Scientists do not yet know which pathway contributed most to the first population of massive black holes. A young black hole could grow by drawing nearby gas into a hot and rapidly rotating disk. Friction within that disk converted gravitational energy into intense radiation before matter crossed the event horizon. The resulting ultraviolet light and X-rays could travel far beyond the black hole's host galaxy. These energetic sources may have heated portions of intergalactic gas before reionization was complete. By this time, glowing bubbles surrounded many early stars, galaxies, and actively feeding black holes. Within each bubble, energetic radiation had removed electrons from neutral hydrogen and changed the gas into plasma. Between the bubbles, broad regions of neutral hydrogen still absorbed much of the light passing through. The universe became a patchwork of transparency and shadows spread across the expanding cosmic web. As more galaxies formed, their ionized bubbles expanded and began overlapping with bubbles created by neighboring systems. Neutral islands grew smaller, although the transformation unfolded at different rates in different regions. This long transition is known as cosmic reionization, one of the major changes in the history of matter. Its precise timing, duration, and dominant sources remain active questions in modern astronomy. We cannot watch this transformation directly as a sequence unfolding across a nearby sky. Instead, astronomers compare light from objects located at many distances, and therefore seen at many cosmic ages. Each ancient galaxy provides one fragment of a history assembled from countless faint and incomplete observations. Together, those fragments reveal a universe becoming brighter, more structured, and chemically diverse. The James Webb Space Telescope has revealed remarkably luminous galaxies from very early chapters of cosmic history. Some appear more developed or more active than earlier models had led many astronomers to expect. These discoveries do not erase the standard picture of galaxy formation, but they test its details and assumptions. Scientists must determine stellar masses, distances, dust content, and black hole activity before interpreting each source. Computer simulations help connect these observations with the physical processes that telescopes cannot resolve individually. They follow dark matter, gas, radiation, chemistry, stars, and black holes across expanding regions of space. No simulation contains every scale or every process perfectly, so researchers compare different models and resolutions. Progress emerges where theoretical predictions and increasingly detailed observations begin to agree. The universe that began with isolated first stars was now filling with clusters, explosions, and primitive galaxies. Darkness still occupied most of space, but light was gathering into networks shaped by invisible gravity. The smallest islands of starlight were merging into larger systems that could retain gas and sustain repeated creation. In the next chapter, those restless islands will become the first enduring cities of light. The first stars had appeared as lonely flames, but gravity was now gathering their descendants into something larger and more enduring. Across the growing cosmic web, small halos merged while streams of gas continued flowing toward their deepening centers. Where stars once shone in scattered isolation, compact communities of light began forming inside shared reservoirs of matter. These restless systems would become the first lasting galaxies, the earliest cities ever built by gravity. A galaxy is more than a collection of stars suspended together against the darkness of space. It is a connected system of dark matter, gas, stars, radiation, and often a central black hole. Each component changes the others through gravity, heating, cooling, explosions, pressure, and the slow exchange of angular momentum. Even the smallest early galaxy was therefore a complicated environment rather than a simple island of stars. The foundation of every young galaxy was an invisible halo made mostly of dark matter. Its gravity held ordinary matter in place and helped the system survive repeated bursts of stellar violence. As halos merged, their combined gravitational wells became deeper and more capable of retaining heated gas. This growing strength allowed some systems to recover after supernovas had driven much of their material outward. Fresh hydrogen and helium continued arriving along the broad filaments that connected young structures across the universe. These streams followed gravity toward dense intersections where dark matter halos and primitive galaxies were already gathering. Some gas entered gradually, while other clouds arrived during violent mergers between systems of comparable size. The first galaxies grew through both quiet feeding and sudden collisions that rearranged nearly everything inside them. As incoming gas fell inward, it accelerated and carried the memory of motions inherited from much larger scales. The gas rarely moved directly toward the center because even small sideways motions produce significant rotation. Rotating material could flatten into thick and turbulent disks around the densest regions of a young galaxy. These early disks were clumpy, unstable, and constantly disturbed by inflowing matter and nearby gravitational encounters. Inside a gas-rich disk, gravity collected material into enormous clouds, far larger than typical clouds nearby today. Turbulence supported these clouds for a time, but dense pockets continued cooling and collapsing within them. A single unstable region could produce thousands or millions of stars during a concentrated episode of formation. The resulting clusters glowed like bright knots embedded inside a much fainter and more irregular galactic body. Many newborn stars were massive, blue, and hot enough to flood their surroundings with ultraviolet radiation. Their light ionized nearby hydrogen and carved expanding cavities through the dense gas from which they formed. Stellar winds pushed matter outward before the first supernovas added even more energy to the region. A star-forming cloud could therefore begin destroying itself almost as soon as its brightest stars appeared. Within only a few million years, the most massive stars reached the ends of their lives. Their explosions sent overlapping shockwaves across the young galaxy and stirred gas into chaotic motion. Some shocks compressed neighboring clouds and helped trigger another generation of stars along their expanding edges. Others broke through the galaxy and opened channels through which hot gas and radiation could escape. The heaviest elements created inside stars were carried outward with the expanding debris of these explosions. Carbon, oxygen, silicon, iron, and many other nuclei mixed imperfectly into the surrounding interstellar gas. Some regions became enriched quickly, while nearby clouds remained chemically simple for much longer periods. A single early galaxy could contain several generations of stars born from gas with very different histories. As heavy elements accumulated, tiny solid particles could begin condensing within cooling stellar ejecta. These particles formed the earliest cosmic dust, although much of it may have been damaged by later shock waves. Dust absorbed ultraviolet and visible light, then released the captured energy at longer infrared wavelengths. Even a young galaxy could therefore hide part of its star formation behind a dim veil of particles. Dust also helped gas cool and provided surfaces where simple molecules could form more efficiently. These changes allowed clouds to fragment into smaller pieces and produce increasing numbers of low-mass stars. The universe was moving away from the unusual conditions that had produced the first primordial giants. Stellar populations were becoming more diverse as each generation inherited the products of those that came before, yet greater chemical richness did not make early galaxies calm or predictable places. Rapid star formation produced enough energy to lift enormous amounts of gas away from galactic centers. Hot outflows rose above turbulent disks and carried metals into the surrounding intergalactic medium. Some material escaped permanently, while slower clouds eventually cooled and returned in a broad galactic fountain. This circulation connected the life of a galaxy with a much larger environment surrounding its dark matter halo. Incoming streams supplied fresh fuel, while outgoing winds removed heat, matter, and newly manufactured elements. The balance between these flows helped determine whether star formation continued steadily or stopped for a time. Early galaxies lived by exchanging material with the cosmic web rather than remaining sealed from it. Mergers brought another source of change as separate galaxies fell together inside larger shared halos. Their stars usually passed one another safely, but their broad gas clouds collided and lost organized motion. Compressed gas rushed toward dense central regions and could ignite brief but extraordinary bursts of star formation. The merged system emerged larger, more chaotic, and often chemically richer than either galaxy had been before. Repeated mergers gradually assembled galaxies through a process astronomers describe as hierarchical growth. Small structures formed first, then combined into progressively larger systems as cosmic time moved forward. Not every galaxy followed the same path because local density, merger history, and gas supply varied widely. The early universe produced a changing population of compact objects rather than one uniform type of galaxy. Near the centers of some systems, black hole seeds were also gaining mass from surrounding gas. Materials spiraling inward formed hot accretion disks that could outshine every star in the host galaxy. Radiation from these active black holes heated nearby gas and sometimes launched narrow streams of energetic particles. The smallest seeds were becoming engines capable of influencing regions far beyond their event horizons. Some early black holes grew rapidly enough to become quasars within the first billion years. A quasar is an intensely luminous galactic nucleus powered by matter falling toward a massive black hole. Its brilliance can travel across most of the observable universe and reveal gas encountered along the way. These distant beacons allow astronomers to study both ancient black holes and the changing space between galaxies. Scientists still debate how the earliest black holes accumulated enormous masses in such limited cosmic time. They may have begun with unusually heavy seeds, experienced rapid feeding, or grown through repeated mergers. Several pathways may have operated together in different galaxies and under different environmental conditions. The brightest ancient quasars probably represent rare extremes rather than the ordinary history of every young black hole. While galaxies and black holes grew, their radiation continued transforming the neutral hydrogen between them. Ultraviolet photons escaped through openings in galactic gas and entered the wider intergalactic medium. Each successful photon could remove an electron from a hydrogen atom and expand an ionized region. Countless stars working together gradually accomplished what no isolated star could have achieved alone. Ionized bubbles around neighboring galaxies expanded until their boundaries touched and merged across enormous distances. The remaining neutral regions became isolated islands surrounded by an increasingly transparent sea of plasma. Reionization did not occur everywhere at once, because galaxies were distributed unevenly throughout the cosmic web. Dense regions changed early, while quieter and more distant voids may have remained neutral for longer. By studying ancient light, astronomers search for the boundaries between these transparent and absorbing regions. Neutral hydrogen leaves recognizable gaps and absorption features in the spectra of distant galaxies and quasars. The pattern changes with distance, allowing researchers to reconstruct how cosmic transparency developed over time. No single observation reveals the entire transition, but many faint signals can be combined into a history. One important signal comes from radiation associated with neutral hydrogen at a wavelength of 21 centimeters. Cosmic expansion stretches that radiation to longer wavelengths before it reaches radio telescopes on Earth. Mapping its changing brightness could reveal where gas was cold, heated, neutral, or already ionized. The measurement is extremely difficult because nearby radio sources overwhelm the ancient signal by enormous amounts. Infrared telescopes approach the same era by searching directly for the faint light of early galaxies. The expansion of space has shifted much of their original ultraviolet radiation into infrared wavelengths today. The James Webb Space Telescope can separate this ancient light into images and spectra with remarkable sensitivity. Its observations reveal star formation, chemical enrichment, dust, ionized gas, and possible black hole activity. Determining the distance of a faint galaxy requires more than noticing that its light appears unusually red. Dust, aging stars, and strong emission lines can sometimes imitate the colors expected from a more distant source. Spectroscopic measurements provide stronger confirmation by identifying specific features and measuring how far they have shifted. Careful verification turns a faint reddish smudge into a reliable record of an early cosmic age. Early galaxies often appear surprisingly bright, but brightness alone does not reveal how much mass they contain. A brief burst of young massive stars can produce extraordinary light without requiring an enormous mature galaxy. An actively feeding black hole can also contribute radiation that might otherwise be attributed to stars. Astronomers compare many possible models before deciding what combination of sources best explains each observation. Computer simulations offer another way to test how quickly galaxies could have assembled under known physical laws. They follow the growth of dark matter halos while modeling gas, cooling, star formation, radiation, and feedback. The smallest stellar processes cannot all be calculated directly inside simulations spanning millions of light years. Researchers therefore use simplified prescriptions and compare their results with increasingly precise telescope data. The leading picture remains one of gradual structure growth interrupted by intense episodes of rapid transformation. Galaxies accumulated gas, formed stars, expelled matter, merged with neighbors, and then began the cycle again. Through these repeated events, small luminous knots became systems capable of surviving across billions of years. The first cities of light were never finished, because every generation rebuilt them from inherited material. By the end of cosmic dawn, the universe no longer resembled the smooth darkness that followed the ancient afterglow. Galaxies now occupied the densest intersections of a vast web filled with stars, metals, dust, and black holes. Their light had transformed intergalactic hydrogen and opened clear paths across regions once hidden behind neutral fog. In the final chapter, we will follow this awakening toward the galaxies, worlds, and night sky surrounding us today. The first cities of light had emerged, but the long transformation of the universe was not yet complete. Between young galaxies, broad islands of neutral hydrogen still waited beyond the reach of ultraviolet starlight. Generation after generation added new stars, new explosions, and new sources of radiation to the growing cosmic dawn. Slowly, the scattered awakening became a change that reached almost every corner of intergalactic space. Ionized bubbles continued expanding around galaxies until their boundaries joined across millions of light years. The remaining neutral regions became smaller, more isolated, and increasingly surrounded by transparent plasma. By roughly 1 billion years after the beginning, most intergalactic hydrogen had been ionized once again. The universe had become a place where light could travel freely between the growing populations of galaxies. The end of reionization did not end cosmic change, because gravity continued building larger structures from smaller ones. Galaxies followed the invisible architecture of dark matter and gathered along filaments, walls, and dense intersections. Small groups became richer communities, while the largest concentrations slowly developed into enormous galaxy clusters. Between these crowded regions, expanding voids remained dark and quiet across almost unimaginable volumes. Within individual galaxies, turbulent matter gradually began settling into more recognizable arrangements. Some systems developed rotating disks where gas continued forming stars along broad and slowly changing patterns. Others lost much of their cold gas and became rounder collections dominated by aging stellar populations. Mergers, gas supply, environment, and black hole activity helped guide each galaxy toward a different future. The Milky Way also began as smaller structures that merged and exchanged material over billions of years. Its oldest stars preserved motions and chemical patterns inherited from systems that no longer exist separately. Streams of ancient stars still move through the galactic halo as faint remains of long-completed collisions. Our galaxy is not a finished island, but the continuing result of cosmic growth and reconstruction. Some of the Milky Way's oldest surviving communities are dense and nearly spherical globular clusters. Their stars formed when the galaxy was young and the supply of heavy elements was still limited. These clusters orbit far from the bright galactic disk and carry memories of an earlier Milky Way. They are not the first stars, but they are among the oldest witnesses still shining nearby. As generations of stars lived and died, the chemical richness of galaxies continued to increase. Supernovas spread oxygen, silicon, calcium, and iron, while aging smaller stars released carbon and other elements. Neutron star mergers and certain stellar explosions contributed some of the heaviest nuclei found in nature. The simple universe of hydrogen and helium became a universe capable of building extraordinary complexity. Inside enriched molecular clouds, dust grains gathered coatings of ice and moved through cold regions of gas. When new stars formed, rotating disks of leftover material often remained around their bright young centers. Tiny particles collided, joined, broke apart, and joined again within those wide disks of gas and dust. Given enough time and favorable conditions, small grains could become the foundations of planets. More than 9 billion years after the beginning, one enriched cloud collapsed inside the Milky Way. Most of its material gathered at the center and ignited as the star we now call the Sunday. The remaining disk produced planets, moons, asteroids, comets, and countless smaller pieces of ancient matter. One small rocky world formed where liquid water could later remain across much of its surface. The atoms inside Earth did not come from one star or one single dramatic explosion. They were assembled through many stellar lives, deaths, collisions, and journeys across the galaxy. The oxygen in rock and water was forged by stars that disappeared long before the sun existed. The iron within Earth carries the legacy of nuclear furnaces and catastrophic stellar endings. Carbon chemistry became possible only after earlier stars transformed primordial matter and returned it to space. Those atoms crossed interstellar clouds, entered new stars, and became part of later planetary systems. There is no straight path from one first star to any particular object on Earth today. Yet the first stars began the chain of enrichment that made rocky worlds and complex chemistry possible. The calm night sky now contains every stage of the long story that followed cosmic dawn. Nearby stars shine through enriched gas, while distant galaxies reveal light from much earlier chapters. Some photons began traveling before Earth formed and continued across expanding space until reaching our instruments. To look deeply into the universe is to arrange ancient moments across a single field of view. A nearby galaxy appears as it was millions of years ago, rather than as it exists now. A much more distant galaxy may appear as it was when the universe was still very young. The sky does not show one universal present, because every distance carries a different travel time. Our view of space is therefore also a layered archive of cosmic history. The oldest light observed across the entire sky is the cosmic microwave background. It preserves the universe as it appeared before the first stars and galaxies had formed. Tiny variations within that afterglow reveal the seeds from which later structures eventually grew. Between that ancient image and the earliest known galaxies lies the difficult frontier of cosmic dawn. Astronomers hope to map this frontier using the faint radio signature of neutral hydrogen. That signal could trace gas before the first stars, during early heating, and throughout reionization. Its patterns may reveal when the first sources appeared and how their influence spread across space. Extracting it remains difficult because human technology and nearby cosmic sources produce much stronger radio emission. Infrared observatories search for the galaxies that supplied much of the light during this transition. The James Webb Space Telescope observes ancient systems whose light has been stretched by cosmic expansion. Its sensitive instruments reveal faint shapes and spectra that earlier observatories could not examine in detail. Each observation brings the era of first galaxies closer without making its mysteries disappear. Nature occasionally provides additional help through the gravitational lensing created by massive foreground objects. A galaxy cluster can bend and magnify light from a much more distant source behind it. The magnified image may appear stretched, duplicated, or brightened beyond what the source could provide alone. Rare alignments may someday reveal stellar populations that would otherwise remain hidden beyond direct detection. Images show where ancient light appears, but spectra reveal more about the source that produced it. Specific features can indicate hydrogen, oxygen, carbon, and other elements within distant gas. Their shifts reveal cosmic distance, while their strengths provide clues about temperature, density, and ionization. Through spectroscopy, a faint point becomes a physical environment rather than only a distant glow. The earliest galaxies observed so far sometimes appear brighter and more active than simple expectations predicted. Their light may come from rapid star formation, unusual stellar populations, active black holes, or several sources together. Distance estimates and stellar masses can change as stronger spectra and improved physical models become available. The evidence is advancing quickly, but careful interpretation remains more valuable than dramatic certainty. Computer simulations allow researchers to test how galaxies might grow under different physical conditions. They follow dark matter across enormous regions while approximating the smaller processes inside stars and gas clouds. When models produce galaxies unlike those observed, their assumptions can be adjusted and tested again. Understanding improves through the patient conversation between mathematical prediction and ancient light. One major uncertainty concerns the exact nature of dark matter, which shapes structure without revealing its identity. Another concerns how efficiently radiation escaped from young galaxies into the intergalactic medium. Researchers also study how stellar explosions regulated small galaxies by removing or compressing their gas. These uncertain details can change when stars formed and how rapidly cosmic reionization progressed. The origin of the first massive black holes remains another unfinished chapter of the story. Some may have grown from the collapsed cores of early stars, while others began as heavier seeds. Their radiation may have heated distant gas and contributed to the changing state of the young universe. Future observations may reveal how these dark engines grew beside the first enduring galaxies. The creation of heavy elements and planets did not guarantee that life would eventually appear. It only created environments where chemistry could become more varied than the primordial universe allowed. The path from simple molecules to living systems involves questions that astronomy alone cannot fully answer. What Cosmic Dawn provided was not certainty, but the material foundation for possibilities that came later. There is something quietly remarkable in the distance between the first hydrogen clouds and the present sky. Gravity followed simple rules, yet those rules produced stars, galaxies, elements, planets, and countless unexpected forms. Complexity did not arrive in one moment, but accumulated through repeated cycles of creation and destruction. The universe became richer because nothing within it remained unchanged forever. Some photons released by the earliest stars may still be traveling through the universe today. Expansion has stretched them into faint infrared wavelengths and scattered them among brighter later sources. Most cannot be traced back to individual stars, but their collective influence remains written across cosmic history. Their light-heated gas altered chemistry and helped transform a neutral universe into a transparent one. The first stars are gone, yet the changes they began continue inside every active galaxy. New stars still gather from enriched clouds and return altered material when their lives are finished. Galaxies still merge, black holes still grow, and the cosmic web still guides matter through space. Cosmic Dawn was an ancient beginning, but its processes have never truly ended. When we look toward the Milky Way, we see light shaped by nearly the entire history of the universe. Every bright star belongs to a generation made possible by stars that came before it. Every dark cloud carries material that has traveled through places and events we will never identify. The familiar sky is the quiet surface of a history filled with fire, gravity, and transformation. Before the first star, there were no galaxies, no planets, and no distant constellations crossing the darkness. Then gravity gathered the first clouds, fusion awakened, and isolated flames began changing everything around them. Their descendants became galaxies, their ashes became worlds, and their ancient light became part of our sky. This was the long night when the universe learned to shine